Okay, so we've talked about chemical formulas already, but I do always like to go back because this is what we're going to be spending a lot of time on. I want to make sure we're sort of on a level playing field or caught up mentally where we should be at. So in a chemical formula like this one for magnesium nitrate, okay, there's a symbol for magnesium. The implied subscript of 1, right? And then we have a symbol for the NO3 minus group, and I'll talk about that. That's actually sort of what we're going to sort of expand on this idea. So here's nitrate, okay? And there's an implied subscript here. There's a 3 here. And there's a subscript 2, and this actually indicates that you have 2 nitrate groups in the formula. And the reason that's important to think about it like this is because this 2 multiplies everything on the inside. So in fact, there's 3 oxygens here, but in total, because of the 2, I have a total of 6 oxygens, right? And then for the nitrogens in total, there's a 1 implied here, but then there's a 2, so that's going to give me, no, that's 60, sorry. I'll do that. 60 oxygens, 6 oxygens, I don't know. It's 2 nitrogens like this. Okay, so how do you know, and this is what we call a polyatomic ion. And when we name polyatomic ions, it's different than when we name monatomic ions. I kind of blew through it a little bit in the earlier chapters, but when we name a monatomic ion that's an anion, we just add the IDE to it, the end. But for polyatomic ions, it's going to be a little bit more complicated. There's just some stuff you're going to have to memorize. And I've done this for, I don't know, a long time, more than 30 years, I think. And I've come up with some ways that I feel like are better for memorizing the polyatomic ions than like you see in most of the books. And so that's what I'm going to give you today. So first thing, though, is you have to be able to recognize when you see a polyatomic ion. And I always do a real simple thing. And I like doing this in the classroom because I can write it, and then I can stick my thumb over it, and it's all clear to you. If I stick my thumb over here, it doesn't block anything except what I see, right? So what I'm going to do is I'm just going to use a blue marker. And so anyways, a polyatomic ion is composed of ions that work together as a group. So these guys go together as a group, okay? Now, to identify a polyatomic ion, it's pretty simple. Block this out, including the subscript, and you look at that and you go, is it polyatomic? What does polyatomic mean? It means it's made up of many atoms. So that's it. That's a polyatomic ion. So many people will fall down on that because you see an S and 4 O's, right? There's 2 different elements there. That's polyatomic. If you do this on number 2, you see 2 of the same element. And there are very few instances where you have polyatomic ions with the same atom in it. So you can assume that this one is monatomic. So whereas there's an SO4 in this group, this whole thing is the ion. Okay, and it actually has a 2- charge, and I'll teach you how to remember that in a second. But where this one is monatomic, it actually has 2 chlorides in it. And again, for monatomic ions, the naming is fairly easy. It's chlorine, right? So you get rid of the INE. And you get rid of this part, and you replace it with the IDE to say that it's an anion, okay? So let's do this other one with mercury. Hg is mercury. And what are you going to do, right? So I'm going to pause. I'm going to do a few things. And when I come back, I hope, or you're going to pause too, hopefully. When you come back, you'll have decided whether or not it's polyatomic or monatomic. Okay, so, right, you cover up the first element and you look at it. Now, ignore that subscript in the brackets. Just look inside the brackets. There's a Cl and there's O's. It's polyatomic. Okay, so it's polyatomic, but just like, right, for the chloride, when there was a subscript 2, it meant there were 2 chlorides. This actually means there's 2 chlorides, so that's the name of this ion, and it's a ClO2 minus. So there's 2 chlorite ions in that compound. This one is sulfate, and again, I'm going to teach you sort of a simple way to memorize about 30 different ions. Okay, now I'm going to pause. You pause again, and you decide what that is. Okay, so what do you see, right? You see one kind of atom. And there are very few, like I said, very few polyatomic ions that have only one kind of atom in it. Now, I should point out, though, one of the ones that is like that, there's actually several of them, is the ones with oxygen. Okay, so I'm going to just put a little note here of the ones you need to memorize that you just have to memorize. O2 minus is known as oxide, which is monatomic. O2 minus is known as peroxide. This is one of the ones that you just have to memorize, and you have to be careful of when you see it. And so this is actually peroxide ion in this compound. So, like I said, when you cover it up, right, you cover up or you knock out that first element, if it has more than one kind of element in it, it's polyatomic. The only time that you have to worry is when you see an oxygen in there, and then it might be peroxide. Okay. Now, how do you memorize polyatomic ions? So take a look at this for a second and notice the layout. I drew a table, right? It's got boron, carbon, nitrogen, and it goes all the way to fluorine, and it goes down all the halogens on the right-hand side. Why does this look familiar, right? Because when you go to this, right, it's this top right-hand corner of the periodic table, and I also filled in the middle parts. It's actually all the nonmetals except for boron as a semi-metal. It's all the nonmetals that we apply this trick to. Okay, so let's go back and I'll tell you what the trick is. Okay, so this is known as the table of eights, okay, ATEs, and that means the anion ends in the phrasing ATE. So, and I'll just write a couple of them for you. Okay, PO4 and SO4 and ASO4 and SeO4. Those are all eights. Now, I'm going to tell you how to remember the charges as well, because you have to know the formulas and the charges. But one of the things that's useful to remember, right, at least as far as I'm concerned, this block in here, how many oxygens do each of those eights have, right? The ATEs, they have 4, and when I first started teaching this, right, I didn't use the SI or the TE, so it was real simple. Those were the 4 eights, and there's 4 of them, and they're in the middle, right? Now, I'm going to show you some more of the eights, and you tell me what the pattern is. And then we're not going to do oxygen or fluorine, and then we're going to do ClO3 and IO3, like that. Now, what's the pattern, right? It's the element symbol, right, with 3 oxygens. And so all the eights on the periodic table, and we'll get to the Si and the Te, okay, are O3 or O4. And the O4s are in the middle, and the O3s are on the edges, right, of this diagram, which is really sort of the edges of what we see on the periodic table. Now, let's do the charge. So the charge can be predicted for many of them just from where they are on the periodic table. But if I was to put a number here, this one would be -1. So I'm going to say 1 minus, right? Now that's also the charge of chloride is a 1 minus. And sulfate, and so this is ClO3 minus. And then sulfide would be O2 minus, and sulfate is SO4 2 minus. And then phosphide would be P3 minus. And then phosphate is PO4 3 minus, like that. So you see that pattern is pretty straightforward. The chloride, the sulfate, and the phosphate, you should be able to predict based on where they are in the periodic table. Remember, chloride, the halogens are over here. This is group 8 over on this side, right? The halogens are over there. The noble gases are over there. And so chlorine wants to pick up one electron to be like the noble gas that it's closest to. So it ends up getting a -1 charge. So sulfur wants to pick up 2, and so it gets a -2 charge, and then phosphate wants to pick up 3, and so it gets a -3 charge. And because of periodic law, and because of position on the periodic table, bromide, selenide, arsenide follow the same pattern. Okay, so I always tell students, if you just copy it down 4 or 5 times, you'll have it memorized. And it's not that hard. You just start drawing. Draw a grid. It doesn't have to be perfect. Throw the scratch paper away. But you do it 4 or 5 times and you'll remember. Okay? And you can quiz each other on it, really. Now, how about the nitrate, the carbonate, and the borate? Okay, that's NO3 minus, CO3 2 minus, and BO3 3 minus. And unfortunately, it doesn't follow the same pattern. There are reasons that you'll learn when we do chapter 10, I think it is, in this book, where we talk about like why it can't be like the others. But for now, we just accept you're going -1, 2, 3, and then the first one we're doing is the nitrogen, so it's -1, 2, and 3. All right. So these represent all the 8. So I'm going to put some names in here just to make sure that I get this out for you, right? This is boron. So it's borate. So get rid of the last part of the name and just replace it with 8. This is carbon, right? So this is carbonate. And then this is nitrogen, so this is nitrate. And this would be phosphate and sulfate and chlorate, and then etc. I'm not going to write them all in because I'm sort of running out of room. But that's how you do all the names. Okay, so that's about half of them. So if the suffix ends in 8, you just look at the periodic table, you look to see where it is, you've practiced it many times. If it's phosphorus, sulfur, arsenic, or selenium, right, they have 4 oxygens and the charge is straight off the periodic table. If it's the others, then it has 3 oxygens and the charge is not straight off the periodic table for all of them, but it's still -1 and then -2 and -3, right? So what about the ites? So the 8s and the ites have 1, right, less oxygen. So if I said sulfate, you would come up with this. And once you have sulfite is 1 less oxygen, and this everything else is the same. So it's still going to be S, it's still going to be O, it's still going to be 2 minus, but now it's just a 3. So now you have the ability to do for borate, carbonate, nitrate, all these guys, and then you can always do all the ites. Okay, so the ites, you just take 1 oxygen off, and that's the same formula. The rest is the same formula, I should say. So what about PO4 3 minus, like that. right? This would be phosphate. Sorry, my dog. I don't know what he's barking at. I think the ice maker. If you want phosphite, it's PO4. Oh, sorry, PO, and it's still 3 minus, but now it becomes 3, like that. Now, I'll actually confess, like phosphite by itself doesn't exist, but there are phosphite compounds which have PO3 in them instead of PO4, okay? So you can apply a rule and name things, and that's going to happen on tests. There's going to be stuff that doesn't exist, but it's going to, if you need to get to the ITE, all you do is you pull out an oxygen, and you leave everything else the same. Now, it's a little bit more complicated with several of the elements, okay? So, for example, this is chlorate, ClO3 minus. And chlorite would be what? ClO2 minus. And it would be nice if that's all that there was, but there's also ClO minus and ClO4 minus. Now the nice thing is the formula structure is still the same. It's the halogen, right? It's an oxygen, and the charge is always the same. And it's just one halogen, right, with the various amounts of oxygens. This is still the 8. We got that from up here, right? We decided that this guy is chlorate. So now, what we can do is say this is the ite, and then we have to come up with something else, right? And what they've come up with is this and this. So if you wanted to shove this one in here, you would just say perchlor 8, and this one would be hypochlorite. So 8 and ite is one oxygen, right? Per is if you have more oxygens, and hypo is if you have one oxygen on the structure. So it turns out for all the halogens, this rule applies, except for fluorine, which doesn't make polyatomics or polyatomic oxoanions. But chlorine, bromine, and iodine all do. It turns out sulfur and phosphorus can also lose more oxygens, okay? So you might see something like this. Oh, and the charge stays the same, right? So this is important in understanding how this works. Now, PO2 3 minus. Well, let's think about phosphorus. If I wanted to name that, right? Phosphorus is in this group here, one of the 4, and it has a -3 charge. So I went PO4 3 minus, and then I went PO3 3 minus, and I went PO2, right, 3 minus. And so this is the 8, this is the ite, and this must be the hypophosphite. Like that. Okay, so that's really it for naming those polyatomic ions. Now, it turns out, if you go on campus, right, there's a page of these. This makes up the majority of the polyatomic ions you need to memorize. And then there's a handful of others, unfortunately, you just have to memorize. And this is usually the point I say to people, what is your middle name? And they tell me their middle name. And I say, well, how did you learn that? And they just said, well, I just memorized it. So some things you just have to memorize. Okay. So we're building up a set of tools for helping us name compounds. So we learned how the formulas are structured. We learned how to identify polyatomic ions, right? We already know how to predict certain cation charges and monatomic anion charges, and part of what we just learned is sort of the structures of polyatomic ions and their formulas. Now, there are several types of compounds, and of these compounds, types. We name them in different ways depending on whether we call them ionic or molecular compounds or covalent compounds. There's two names for it. But depending on how we do that, how we classify these compounds, it's going to change how we go about naming them. So what I want to do next is go through how you identify what type of compound you're dealing with so that you can name it appropriately. So the first type of compound is a molecular or covalent compound. And it's very easy to recognize 99% of the time because it's all nonmetals. So, anything from, oops, sorry. You don't need to see that. You see that. Anything from this top right-hand side of the periodic table, those are the nonmetals that are up in this side over here. Okay, so if that's all that you see in the formula, then it's a covalent compound. Now, covalent compounds, the smallest unit is called a molecule. And that's why we call them molecular compounds too, because and so when somebody says, this thing is made up of different kinds of molecules, that actually has a real meaning to it. That is, it's all nonmetal compounds. These units, right? Some examples like H2O would be one. Hydrogen's not in that top right side, but is definitely a nonmetal, right? But it could be like CO2 or CO or one other interesting one. C6H12O6. These are all covalent compounds. And the thing that's interesting about these is these are like a tight-knit group. They hang out together, and when you put them in water and they dissolve, right, for example, they stay together. They say, hey, these are my friends. I'm going to go out with my friends. And it's the same group of friends all the time. Okay, so maybe you're like that, or maybe you're like an ionic compound, and we'll talk about that in a second. But ionic compounds are easy to recognize too because, really, they're made up of ions, right? So that's kind of goes without saying, I guess. But I said it, so there you go. But the easy way to recognize them is that they have a metal in them, and the metal is the first element, okay? The first element I'm not sure what I'm spelling anymore. Element is a metal. So let's see. Smallest unit. It's actually called a formula unit. And the interesting thing about a formula unit, it's actually usually the simplest sort of representation of the compound. So if you recognize C6H12O6, all those numbers are divisible by 6. And so you could actually, if you divided that by 6, you could get CH2 and O, right? So molecular compounds, you can't really do that because this is not really this. It's not the same thing. You can't break glucose up to make it CH2O. It just doesn't do that. It's a unit. They all go together all the time. But it turns out formula units are not that way, and it's always the simplest representation of a compound. Now, some examples, right? Well, sodium chloride, NaCl. That's one that's probably familiar to you because it's table salt, right? But how do I know that's an ionic compound? Because when I put my thumb, right, which doesn't help you, over that second element, I almost hate doing this. When I do that, you have to ask yourself, is that a metal or a non-metal? You go back to the periodic table, right, over here, and you find sodium, and it's right here. And so you say to yourself, gosh, is that in the group where the metals are? Remember, everything's on the left side of the periodic table is a metal, so sodium is a metal. Now, maybe you don't think about it. Maybe one of these days you can come by the lab and I can actually show you. If you take pure elemental sodium and you look at it and you cut it, it's soft, it's malleable, So it's not like you're thinking like sodium chloride's like white ionic compound. It's soft and malleable. It's shiny on the inside. Okay. It's also very reactive with water, so we keep it in oil and things like that. But it's a very interesting experience to actually see some of these pure elements because they're not exactly what you might have thought they were. And we'll talk about that a little bit when I finish this section, just a little add-on thing. So again, I don't want to just leave it like that. So there's sodium chloride. All right, that would be an example. Magnesium sulfate, like this. That's magnesium sulfate. All right, that's Epsom salts. That is also an ionic compound because of the magnesium in the front. So what we're going to do is we'll do a little bit of practice identifying each as ionic or molecular compounds, and then we'll write whether or not it's best described as a molecule or a formula unit. Okay, so I'm going to pause, I'm going to fill it out, and then we'll talk. So hopefully this is what you came up with. PtO2, that's platinum 4 oxide is actually the actual name of it. But if I cover up everything to the right and I say, is that a metal? And the fact is platinum is a metal, right? So it's an ionic compound and it's made up of formula units. All the others are molecules or molecular formulas. So HCl, these are nonmetals. SO3, those are nonmetals. And CF2, Cl2, those are also nonmetals. So this is how you go about identifying covalent molecular compounds versus ionic. Now, one more thing to talk about is the idea of an empirical formula or a molecular formula. So molecular formulas actually represent the numbers of atoms in the molecule, okay? But an empirical formula is that simplified version that I was talking about before. So molecular formulas, exact numbers of elements in a molecule, and an empirical formula is the simplest formula. And empirical comes from how the formulas are discovered. They're discovered by looking at data. So we collect data and we get a formula. That would be, generally speaking, an empirical formula. So if you look at this formula, this is what I want you to decide. Is that an empirical formula or a molecular formula, right? I'll give you just a second to think about it. And it's got 2 and 6, right? So those are both divisible by 2. So this is molecular. Then what I want you to do is write the empirical formula. So I'll give you 1 second. And if you divide both by 2, right, you're going to get CH3. This is empirical. Now, it's possible that the empirical formula is a representation of the molecular formula, but if it's the smallest representation of the numbers, it's an empirical formula. All right, do NO2. Right, both are divisible by, N2O4. NO2, that was the empirical formula, I just did it in my head. It's N2O4, they're both divisible by 2, so this is a molecular formula. And so the empirical formula would be NO2, because I can divide by 2, right? So I can go like this. This one, I think I divided by 3. No, I did, that's boring, I divided them all by 2. And this one is also divisible by 2, and the empirical formula would be C2H3O, and so this is molecular here. So they're all molecular formulas. I kind of cheated. But these are all empirical formulas, the ones that we derived.